Okay, let's look at these three gases. Oops. We do the experiment. How much volume do these three gases occupy at STP? So this is the experimental data. We just get these gases at 273 degrees Kelvin, 1 mole at 1 atm. What is the amount of volume these gases occupy? 22.4. Doesn't matter if we're talking about this gas, that gas, that gas. Pretty much all these gases kind of behave similarly. So this is why it's called the ideal gas law. That these gases all behave similarly, ideally. So let's do this example. What else can we do with this ideal gas law? We could calculate something called a molar mass. What is the unit for molar mass? Right? From a periodic table means grams per mole, right? So from this information, ideal gas law, let's figure out what is the molar mass of an unknown gas. We have this gas, we don't know what it is, but we know it weighs 4 grams. It has this much volume, and we know the temperature of the gas, and we know the pressure of that gas. So let's figure out, write down what we have. There's a lot of information. We have the mass, temperature, the volume, the pressure. So what do we know about what we're looking for? We're looking for grams per mole. And we're just going to say that equals to capital M or mm, molar mass. We'll just, I guess in this example, they just put one m as molar mass. What do we know? PB equals nRT. What is that N? That is the moles over here. So that's basically grams per mole. I'm going to rearrange this formula and make moles equals to grams divided by M. What am I going to do with this? Because this is N, right? So this is moles. So I'm going to get that unit. I'm going to plug it into here. So PV equals nRT. Instead of putting N, I'm going to put grams per molar mass. That's the definition of mole. So I could calculate for this value M here, right? Do I know the pressure of my gas? Yes. Do I know the volume of my gas? Yes. Do I know how many grams I have? Yes, 4 grams. Do I know what R is? That's a constant. Do I know the temperature? Yes, 296 Kelvin. Then I could solve for capital M, which is in this case, molar mass. And then we arrange the formula, and molar mass equals the grams RT divided by PV. Plug in the numbers. Make sure your units cancel out. Grams over here, R over there, temperature, volume, pressure. All the units cancel out. What's the only units left over? This one cancels that one. Grams per mole. That's what we have right there. So then based on this information, the molar mass is 107 grams per mole. Is this gas oxygen? You know, we don't know what this gas is, but based on this information, is this gas oxygen gas? Yes or no? What do you guys think? Is this gas oxygen gas? Or could it be oxygen gas, this unknown gas? How do we know that? How do we know it's no? Because oxygen is, what's the molar mass of oxygen? That's 16, but there's 2 of them, so 32 grams per mole, which does not equal to 107. So this thing, even though we're not sure exactly what gas it is, but it can eliminate a lot of other choices. So we have to figure out, okay, what gas is 107? Right? So this tells us information of what the molar mass of our gas. So we can, oh, it's not oxygen, it's not H2, it's not H2O. So we know it's going to be this one. Okay. Oh, there's a question on the chat. How do we know 760 torr or 751 torr equals to how much? So we got to do a conversion factor, right? 751 torr. And what do we say? 760 torr equals to 1 ATM. So 751 divided by 760 is that number. So we're always going to have conversion factors all the time, right? Whew. Here's another one. Determine the grams. Okay. Now we got this oxygen gas. This oxygen is in this cylinder, 50-liter cylinder, and we know the temperature of that gas. And when the oxygen pressure, and then we know the pressure, we have a little gauge that says 15.7 atm. How many grams do we have of this oxygen in this tank? So what can we do? Do we know the pressure of that gas? Yes, 15.7 atm. Do we know the volume? Yes, 50 liters. Do we know R? Yes. Do we know temperature? Yes. We solve for moles. Once we know the moles, you think we know how to convert moles to grams? That's right. So in this gas, what are we trying to figure out? The moles. So plug in the numbers. PV equals nRT, solve for N. Oops. Put all those numbers in for N. PV RT. 32.5 moles in that container. But they're asking for grams. So you're the guy who's selling this oxygen tank to this hospital, and the nurse is, you telling the nurse, oh, it has 32.4 moles of oxygen in the tank. You think that nurse is going to know what the heck you're talking about? No. Well, the sales or the person who actually buys that tank or that from you, or the shipping receiving guy, he's going to know what the heck is 32.5 moles? No. So you got to convert that moles into what? Grams. And we know how to do that. 32.5 moles times the molar mass gives us basically 1,000 grams. So now you could just tell the guy, oh, I have 1,000 grams of oxygen in this tank. Oh, that's going to mean something. Something like 32 grams, 32 moles to somebody. It's not going to mean anything. But if you say 1,000 grams, it means something. They'll understand. So based on this information, we don't actually have to weigh the container. We don't have to weigh the oxygen, but we could calculate what the weight is based on the pressure, temperature, volume. Based on this information, I could, instead of weighing the gas, sometimes it's hard to weigh gases. So instead of weighing it, I could calculate it. And then in this tank, we say we have 32 moles or 1,000 grams. How do we double check that? We actually go and weigh that empty cylinder and then weigh the cylinder full, and it turns out to be correct. So now, instead of weighing stuff, we just look at the pressure gauge, and from the pressure gauge and the temperature and from the volume, we could determine how many grams of oxygen is in that tank. Then we could also do something called density. What is density? Density is what? DMV, right? Divided by volume. So density is the mass divided by the volume. So let's do this. Let's do this little exercise here. Molar mass divided by molar volume. What does molar mass mean? Grams per mole, right? What does molar volume mean? Moles per liter. Okay. How many moles per liter? Do we know that for STP? 1 mole will give me 22.4 liters. So 1 mole equals to 22.4 liters at STP. So now I know molar mass means grams per mole. Molar volume, moles per liter. So then what that means, what are we going to do here? This mole cancels that mole. So what's the unit? Grams per liter, which is grams or mass divided by volume, which is density. So we could determine the density of a gas by getting the molar mass of the gas divided by the molar volume. And that gives us a unit of density, grams per liter. Wow, that's pretty interesting. Let's see if that's actually true. Let's do an experiment. So, what's the density of helium? Molar mass, 4. Where did I get that unit 4 from? From molar mass? From the periodic table, right? And this gas is going to be, this density is going to be determined at STP. So we know at STP, PV equals nRT, the volume is going to be 22.4 liters per mole. That's what we put on the bottom. So do the math, and this turns out to be 4 divided by 22. This is the density of helium, theoretically. Then we'll go in the lab, and we could determine the density of helium, and that matches up with the theoretical number. To the density of nitrogen, molar mass of nitrogen is 28 divided by 22.4, 1.25 grams per liter. And we do go in the lab, that happens to be correct. So what do we notice here? The bigger the molar mass, the higher the density. So density is proportional to molar mass. So the bigger the molar mass for a gas, the more dense it is. Any questions or comments so far? So all these equations are turning out to be true when we do the experiment. This is the density of helium, this is the density of nitrogen, and we could predict it just by getting the molar mass divided by the 22.4 liters per mole. Now, if I want to know the density of all these gases, do I have to do all these experiments? No, I could just use this formula. Right? To do an experiment, like doing density of a gas, could take you like several days to do that experiment. Okay? So just by doing the calculation, it makes life easy and it gives you the true value. All right. So I want you to look at this one. Vote A, B, C, or D. Which of the following gases is the most dense? Let's see. Let's just see. All right. So density equals to molar mass divided by 22.4 liters. So which one of these has the highest molar mass? This has a molar mass of 2. This one has a molar mass of 28. This one is 32. This one 32 plus 14, 44. So which one has the biggest molar mass? This one, C. That's going to be the most dense. So if we're in a lab, we'll be talking about a fire extinguisher. What's inside a fire extinguisher? CO2. Why CO2 in some fire extinguishers? Because you spray a fire. What does a fire need to burn? It needs oxygen, right? So when you spray with CO2, CO2 is heavier, more dense. So is CO2 going to go to the bottom or on the top when you spray the gas? It's going to go on the bottom of oxygen. So CO2 is going to come on the bottom and push this oxygen up. So now the fire has no more oxygen to burn, and that's one way. This is how a fire extinguisher kind of works, or one of the way it works. There's many types of fire extinguishers. So one of them has CO2, pushes the oxygen away from the fire, and if you have no oxygen, you have no fire. So that's the principle behind some fire extinguishers using CO2. Okay, then got something called partial pressures. What does that mean? So there's a, what is the total pressure of a gas? Is suppose you have a mixture of gases like air. Right now we're breathing in air, but what's in the air? We have nitrogen, oxygen, CO2. So what's the total pressure? The pressure of nitrogen plus the pressure of oxygen plus all these other pressures. So when you add up all the pressures, that's going to give you the total pressure when you're talking about a mixture of gases. So look at the individual pressures, add them all up. That's going to give you the total pressure. And what do we know about pressure? P equals nRT divided by V, right? So this gas is going to have a pressure. This one's going to have a pressure. That one's going to have a pressure. So what we're going to do is, instead of putting P, let's put in this whole thing into here, into here, into here. That's what we did on this step, the second step. So what we notice is when we do some mathematics, oh, look at the common variables. Then we could take them out. So we could put RT, all of these three gases are going to have the same R value. They're going to have the same temperature, and they're going to occupy the same volume. So then it simplifies to this equation. So total pressure is basically related to total moles. So if you know the total moles, you're going to know the total pressure. So it basically means if you know the moles, you know the pressure. So if you know the pressure, you know the number of moles. So when we, you heard like a COVID, people have to get this oxygen tank and they have to breathe in oxygen, or like, people sell oxygen. Why do people sell oxygen? Don't we just breathe it in from the air for free? How do people put oxygen, pure oxygen, into a tank? Anyone know? So I'm supposed to have a little tank. How am I going to put pure oxygen into here and then sell it, right? So imagine this is a tank, got pure oxygen. How am I going to fill it up? I'm just going to grab the oxygen with my hand and then push it in, squish it into that tank. So very common ways to do a chemical reaction. So this is just one example of a chemical reaction. And this one's zinc plus HCl. And then you get these bubbles from the reaction. And what are these bubbles? It's H2. So this gas, we're producing something called H2. And when we produce bubbles, what's going to happen? These gases are going to expand. And where are these gases going to go? You have to trap it somewhere. So what I'm going to do, I'm going to get a cup of water. And I'm going to get a piece of glass like this. And then I'm going to flip it upside down. When I flip it upside down, I got my water level is going to be all the way up top. And what I'm going to do, I'm going to get this gas, and a tube, and I'm going to get that tube over here. And what happens when the gas fills up this area? What's going to happen to the water? Water is going to go down. That's how we trap the gas in this little space right here. It's filled up with water, and now I put in this hydrogen gas from this chemical reaction, and it's pure hydrogen because it's from this chemical reaction, so I don't have to purify it. It's pretty much pure, and it's going to go into this container. The more I have in there, it's going to push the water out. Oops. And then that's how we trap the hydrogen in this spot right here. So if you're in a lab, we would be doing something like this, but we're not in the lab. So how much hydrogen do we have in here? Do we know the volume of this container? Yes. Do we know the temperature? Yes. We know the pressure? Yes. And then, but what's in this? What gases are in here? Anyone know what type of gas is in here?
Hydrogen.
Hydrogen? Anything else?
Molecular hydrogen.
Suppose I have a cup of water, right? I have this much water in my cup.
Water vapor.
After 1 day, is my cup going to be the same level of water or less or more water?
Less.
Why less?
It evaporated.
Water evaporated. So remember, we're doing this over water, right? So I think someone mentioned the right answer earlier. What's going to happen to the water? It's also going to evaporate. And we're going to have, what's in the gas here? It's going to be hydrogen plus water vapor or water gas. Because why? Because water is evaporating, right? So we're going to have two gases in here. Probably more hydrogen, probably very little oxygen, very little water, but we're going to have two gases.
You would have to freeze it in order for it to turn to a liquid then for the hydrogen.
What do you want to do?
Say like, because hydrogen can be a liquid too, you know, and they store it in a tank, like liquid hydrogen. So, so you'd have to freeze that to make it to a liquid. It would have to drop it to a colder temperature.
Yeah, I'll give you an example. Your job is to get this gas and sell it to somebody, right? So when you sell it to somebody, you have to put it in a container. Is that right?
Yes.
So if, hold on a second. When I sell it to somebody, is it easier to sell it to somebody in a small container like this or in a really big container like that? Which way do you think it's easier to sell it to somebody? A small container that's like the size of my hand cup, or container that's bigger than my house? Which one you think is easier to sell? Something that's as big as my house, or think something that's big as like this little cup? A cup, right? So what do we got to do? I'm going to compress the gas. Because if I just have the gas by itself, it's going to occupy the size of my house. I need a box as big as a house, but that's not practical. So what am I going to do? I'm going to compress the gas. Because what are gases? The space between the gases are very small apart, very far apart. So what I'm going to do, I'm going to compress it. When I compress it, I could put it into this container, small container, compress. What happens when I compress it? The particles are going to go farther apart or closer together?
Closer.
Closer. When I put these particles closer together, do they behave like a gas or they behave like a liquid or a solid?
Like a solid and a liquid, you're right.
Yep. So when we compress it, now the gap is going to be very small. So look at this equation, PV equals nRT. So when we compress it, it's very, 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 very small. So then, I don't know if you ever like get some type of like a, I don't know, maybe think about your, like a can, and you spray it, open it up, and some gas comes out, right? But when you shake it up, you hear there's a liquid in there. Why is it a liquid? Because that container is compressed. So now you got this thing in the container is compressed, and your question was, do I have to make it cold? Nope. You just have to compress it. And then what happens when this gas comes out of the container? What's going to happen to the pressure when the gas comes out? What happens? The pressure goes what, up or down? When the gas is all compressed here, the liquids, they're all next to each other, but when they come out, the particles are going to become like a gas, be spread out, right? Does that make sense? Pressure is going to go down. What happens when pressure goes down? Temperature goes down. Because N is a constant, you have the same number of moles. R is a constant, so when pressure goes down, temperature is going to go down. So it's going to get cold when it gets released. So that's when you think about things are going to get cold. When it's compressed, when it gets released, that's when it becomes cold. Okay? Hopefully that makes sense. All right, so in this here, we got vapor pressure. This water is evaporating. So we call that vapor pressure. Because can a solid or liquid have pressure? No, only gases have pressure. Right? So we call that vapor pressure. So the higher the vapor pressure, that means the more it wants to become a gas. The lower the vapor pressure, it doesn't want to become a gas. So higher vapor pressure, more likely it wants to become a gas, because that's what the definition of pressure means, kind of become a gas. So you look at this, someone measured all the pressures of the vapor pressure of water at different temperatures. So 0C, what is the vapor pressure? 4 torr. Millimeter mercury is the same thing as torr. As the temperature gets hotter, what's happening to the pressure? It's getting bigger. So right now at room temperature, if this was like really cold, it's going to evaporate a little bit. But in my cup, if it's a nice warm day, the water is going to evaporate more. Right? So the higher the temperature, the more evaporation we have. That's why you notice like on days that are very humid, it's also very hot, because hot days are making the water evaporate. So what we notice is when it gets hotter, the pressure gets more. Right? The more pressure, the more evaporation. And then right here at 100 degrees Celsius, the vapor pressure equals to the atmospheric pressure. So when the vapor pressure equals to the atmospheric pressure, that is called boiling point. The water is always evaporating at different temperatures, but when you get to 100 C, it's called boiling because the vapor pressure equals the atmospheric pressure. So, do we know the pressure? Do we know the vapor? We know the pressure of the water in here, vapor pressure. If we know the temperature of this gas, yes. We just look at this table. Oh, temperature is 25 degrees. Then the pressure of the water in there is 23.78. So if we know the temperature, then we know the vapor pressure of that water. So here, we could get a little container. This is, we get a little dial here, pressure gauge, and the gauge is saying, I don't know what it's saying, 720 torr. That's the total. So I must mean the water is occupying maybe 20 torr, and then the rest is from the H2. So we could get a pressure gauge like this, measure the total pressure, and we know there's water in there. We know the temperature of the water, so now we know out of the 720, how much of it is water? Oh, 23 pressure is from the water, and the rest of it has to be from the H2. So this is kind of the experiment. HCl plus zinc is going to give us H2 gas. Determine the mass of hydrogen collected. 156 mLs of glass is collected at 19 degrees Celsius, and the total pressure is 769 torr. We want to know how much hydrogen did we collect, because that's what we have to sell, right? So I have to tell the customer how much hydrogen is in this tank. But the tank is 156 mLs. So how many grams of hydrogen do we have? So well, we know the total pressure. Right? Total pressure equals to the pressure of H2 gas plus the pressure of my H2O. Do I know the pressure of my H2O of water? Yeah, I just go on my table here. Well, it doesn't have 19, but this one has 20. So what's my pressure? It's going to be about less than this number, about 17.55. Might be a little bit lower based on this table. So I know the pressure of my H2O, right? And I know my total pressure. Now I could calculate this one, right? I could calculate the pressure of H2. If I know the pressure of H2, then I know PV equals nRT divided by volume. Do I know my volume of my gas? Yes. Do I know the temperature? Yes. Do I know R? Yes. So then I solve for N. Once I solve for N, then I know how many grams I have, right? Because once I know the moles, I know how to convert moles into grams, right? So remember, everything you learned on week 1, you need for week 2. Week 2, you need for week 3. So all this concept about moles and mass, you still need to know. So that's kind of the pathway how to solve this problem. Total pressure equals to pressure of hydrogen plus pressure of H2O. Well, we know the pressure of H2O. You just look it up in a table, and that's this number. We know the total pressure. So now we could just solve for pressure of H2, which turns out to be 72 or 752 torr. And we know how to convert millimeter mercury into ATM. Why do we need to do that? Because remember, PV equals nRT. The units of R is an ATM, has an ATM in there. Oops. So 752 divided by 7C equals to 0.989 ATM. Do I know the volume? Yes. This many liters. Do I know the temperature? Kelvin? Yes. Now I solve for moles. We look at our R value here. R value has liter, ATM, K, mole. So that's why our pressure has to be in ATM to cancel out with this ATM. Our temperature has to be in K to measure to cancel out with that K. Then we solve for N. Do we know the pressure? We know the volume. We know R, we know T. And this is how many moles of H2 we have in our tank. So we know how to convert moles into grams, right? This many moles times the molar mass. This many grams of H2 is in our tank. All right. Because if you want to know experimentally, if you want to weigh out this, you think it's going to be easy to weigh this gas out over here? We weigh it out, then some of that weight is going to be oxygen, some of it is going to be hydrogen. So weighing gases is not so simple. It's a lot easier to measure the pressure, and then from the pressure, determine the number of moles. And once we have the number of moles, determine the grams. You guys okay? You guys still alive?
Trying to absorb.
Absorb, good. So biggest way to try to absorb is read for class, right? For lecture. It's easy
The
to say,
recorded
but
lectures help.
go ahead.
I said the recorded lectures help because like we're in a normal class. All we can do is look at the slides, but then we have our lecture. So that's been a little bit helpful.
Okay, good, good.
It is pretty good because you sync up when you go back and you can actually get the understanding more.
All right, great. I'm glad it's working out. Maybe I'll just have these recordings and then I'll save them, and then future classes I just do the recordings only.
Well, next semester, professor, just press play, go back to sleep. But you know what's, it doesn't show your active, like we can hear you, but on the lecture you're not there, so they might catch on. And plus they can't ask you questions.
Yeah. I'll have they'll listen to the recordings, and then they might meet me in school and they go, oh shoot, like you're like 70 years old, and then on the video you look like so young. Like 20 years ago.
That's really, there's actually a programming, it's like it's an artificial intelligence, and it can identify your question matter, and it can now respond pretty accurately, even to trick questions like how many can a human have 17 arms, which before would trick up AI, but now it doesn't. So you could integrate that, professor.
Nah, it's okay. I'm kind of old-fashioned, so I don't do that. I think that's kind of I know the technology is there and everything, but I don't think that's right. That's not the right way to do things. All right. All right. So now, that's good. I'm glad the recordings are helping. All right. Reactions involving gases. So now, remember our old friend, stoichiometry, limiting reactants? Now before, we could just add liquids together and solids together and do a chemical reaction. Now we could add gases and do a chemical reaction. Right? So what are chemical reactions? We need to know the moles. Oops. Right. Oops. Wow, this is getting a little glitchy. I lost my pen. Okay, got it. So PV equals nRT. We get the moles of the gas, right? If you know the moles of the gas, then we could do limiting reactants. We could do stoichiometry, right? So now we could do chemical reactions with gases. So remember, these are my reactants. These are my products. If I know how many moles of reactants I have, I know how many products I can make. If I know how many moles of reactants I have, I know how many grams I have, right? If I know how many moles, I know how many molecules I have. If I know how many moles, I know the volume, right? PV and RT. If I know the moles, I know the volume of the gas. If I know the moles of product, if I'm making a gas, then I know the volume of gas I'm going to make. So if I know one of these boxes, I know how to calculate all of these boxes, the values. That's just to give you a little hint. You guys understand what that hint means? So here's some simple calculation. Convert moles and volume using the molar volume if the conditions are STP. If you're at STP, we already did this calculation. 1 mole equals to 22.4 liters. If we're not at STP, then 1 mole will give you a slightly different value. But since we are at STP, we already did this calculation. So use the ideal gas law if the conditions are not at STP. All right. So here's this stoichiometry, our old friend. What volume of oxygen at 760 torr and 25 degrees Celsius are needed to completely react with 3.2 grams of ethane? Man, this is a long one sentence, but I just read it and I don't understand what the heck they're asking, so I got to read it again. What volume of oxygen? This is what they want. P. At this pressure, this temperature are needed to completely react with 3.2 grams of this. I got 3.2 grams of that. But then how much of oxygen do I need? 2 of this will need 7 of oxygen. What does that 2 and 7 mean? It means moles. So I got to convert that 3.2 grams into moles of this. Once I know the moles of my ethane, then I can figure out how many moles of oxygen I need. Once I have the moles of oxygen I need, then I can calculate the volume of oxygen. Okay? So write down what we know. Mass, temperature, pressure. So 3.2 grams of ethane, convert that into moles, times that by the molar mass. Now I got moles of ethane. But do I want moles of ethane? I want to know the moles of oxygen. So I got to put O2 on top, right? Ethane on the bottom. It's going to be 7 to 2 ratio. 7 to 2 ratio. 7 to 2 ratio. Where do we get that 7 and 2 from? From the balanced chemical equation. Moles of oxygen. This many moles of oxygen, right? Is that what the question is asking for? No, they're asking for the volume of oxygen. So I know how to convert moles to volume using PV equals nRT. PV equals nRT. PV equals nRT. And V equals nRT divided by P. I know moles, I just calculated that. I know R, I know T, I know the pressure, and I solve for V. That's what we did over here. 9.1 liters. So if I have 3.2 grams of this compound, I need 9.1 liters of oxygen to react with this compound. So back, same thing as stoichiometry. Now we're dealing with a gas. We could use volume. Here's another one. Oh, long sentence. I'm not really a good reader, so I have to read things over and over again to understand what it means. So why don't you guys read this for 30 seconds, and then let's see if anyone understands what this question is asking. Oh, while you guys are reading, let's take a break. It's a good time to take a break. Let's meet back at 10:15 a.m. and we'll see you in 10 minutes. All right, we are back. So let's see what is this question asking for? Suppose you're an engineer, and you're designing a car, and you need to make an airbag. And then you know how airbags work in a car? Suppose you have like basically this little balloon, and then what happens if the airbag gets too big? What happens to the airbag if it gets too big? Anyone know? Maybe nobody's here yet, back from the break. It pops, right? How about if I don't have enough air in that airbag? What's going to happen to the airbag? Is it going to help protect you? Nope. I have too much air in the airbag, or else the airbag is going to pop. You can't have too little, and then it's not going to work. So you're an engineer at the company. Your goal is to figure out how much air has to be in that airbag. And they figured out, I need 75 liters of gas in that airbag for that airbag to protect you, right? So we need to figure out, okay, now you got this airbag. It's not inflated. I got to put a little chemical in here to make this airbag fill up to 75 liters. Am I going to put a lot of chemical or a little bit of chemical? That's what you have to figure out. So in this airbag, I want to produce 75 liters of this guy because this is your G, your gas. I want to produce 75 liters of this gas. How much of this do I have to put in? If I put in too much, I'm going to produce too much gas. The airbag will blow up. If I don't put enough, my airbag will not inflate, and then if there's an accident, it's not going to protect me, right? So now the goal is, how many grams of this do I need? And this is basically back to our stoichiometry. 6 moles of this is going to produce how many moles of this gas? 9. But how many moles do I need to produce of this gas? I don't know. I need to produce 75 liters. So I got to convert that 75 liters into what? Moles. Once I know the moles of nitrogen, then I can figure out how many moles of this guy I need. Once I know how many moles of this guy I need, then I can calculate the number of grams. So it's kind of like working backwards. So we have 75 liters. I got to convert that 75 liters into moles. Erase this. The goal is to determine grams, but they give us 75 liters. So this is the map we drew up before. Write down what we know. Do we know the pressure? Yes. R, yes. Volume? Yes. Temperature? Yes. Moles? No. We have to calculate the number of moles. So PV equals nRT. Solve for moles. Do we know the pressure? Yes. Volume? 75. R? Yes. Temperature? Yes. Oops. So we got 3 moles of gas that we need to make. So this is how much we need to make, 3 moles of this. How much of this, so how many moles of this do I need? To our stoichiometry, 3 moles of our product. I put N2 on the bottom, sodium azide on top, 6 to 9. 2 moles of the sodium azide. This is how many moles I need. But the question is, I don't want the moles, I want the grams. So now we know how to convert moles into grams, right? 2 moles times the molar mass of the sodium azide gives us 131 grams. So that's how many grams of this compound I need to put into this airbag. So it will inflate, right? So who's putting this grams into this airbag? You think it's some chemist? No, it's some factory worker, some worker at the factory. You're giving him instructions. If you tell him, oh, put in 2 moles of sodium azide into this bag, that factory worker is not going to know what the heck you're talking about. So you have to tell him you have to put in 131 grams of this chemical into this airbag. And then he'll be able to understand that and do it. Right? But how do we get to that 131 grams? We have to have a balanced chemical equation, right? Do our stoichiometry, determine the moles, and once we have the moles, we know the grams. So this is pretty much everything you learned before, but we're just adding one more step in terms of giving you the volume, converting the volume into moles. All right. So this is basically how your airbags work in your car. Pretty much the same, this chemical actually. And when it reacts with this iron oxide, it produces gas really quick. And that's how your airbag gets filled up really quickly. So not enough gas, it won't protect you. Too much gas blows up the airbag. And what happens if I have this chemical reaction, but inside this airbag, this small airbag, then it's going to, later on, it's going to expand into this really big airbag, right? What happens if they put a little piece of metal right here, sharp piece of metal in that airbag? And what happens when this airbag gets filled up, what's going to happen to that little sharp piece of metal? Anyone know?
Well, it's dangerous, isn't it? Basically like a bullet.
Yep, that gas you just produced is going to shoot that bullet, that piece of metal, through this airbag and into where?
Your face, I guess.
Your face. Yes. So that's why you ever heard like airbags getting recalled from some cars? People
Yes.
dying from airbags. Yep. There's like a piece of metal, from somewhere, I don't know where. When the airbag explodes or pushes the air, it's going to push this piece of metal straight through this airbag, straight into your face. You think it's going to happen really slowly, or it's like a bullet? Probably faster than a bullet hitting your face. All right. So we call this ideal gas law, assuming that all the gases behave similarly. What assumptions do we make? There's no attraction between the gas molecules, and the gas molecules really don't take up that much space, each particle. And if you look at real gases, here's some real, real gases, and these are some real experimental numbers. 1 mole, how much does it occupy? This one, 22.06, 22.3, 22.4. So they're all pretty much spot on. There's a little variability with some other chemicals, but they're pretty much on the same. There's some slight differences for different gases. So why is there slight differences for real gases? These are all pretty much the same, but some of them are a little bit off, maybe a little bit more for this one. So, to give you an idea, so this is the molar volume, and this is the pressure. So this red line here is like an ideal gas. This green one here is a real gas of argon. When these two lines are right on top of each other, the PV equals nRT matches up exactly with the real gas. Exactly. But out here, there's a gap between these two lines, so they're giving me different values. But over here, the PV equals nRT is like a perfect match. But PV equals nRT doesn't work out here. What do you notice out here? What's the pressure we are under right now in LA?
Gravitational.
Give me a number. What's our pressure right now? One ATM. Where's one ATM on this plot? Way over here, right? When does a real gas and an ideal gas, they don't match up? When does PV equals nRT doesn't work? At 200 ATM. Right? Under 200 ATM, it's pretty much a perfect match, but over 200 ATM, it doesn't work anymore. Why is that? What happens when you put a lot of pressure on the gas? Do the particles come closer together or farther apart? Oh. Yeah, they come closer together. When these particles come closer together, is it going to behave like a liquid or is it going to behave like a gas? When you put it closer together. Yeah, more like a liquid. So this ideal gas is not going to work because ideal gases is for gases. But if you put a lot of pressure, they're not behaving like a gas anymore. Now they're behaving a little bit more like a liquid, some liquid property in there, right? So that's why we have a little gap in here. Ideal gases don't work at high pressures. This PV equals nRT doesn't work at these high pressures because at high pressure, these molecules are really close to each other, and maybe it's not a real gas anymore. Maybe it has some property, a little bit of liquid properties in there, right? So, but when you're talking about, normal pressure, 1 atm, ideal gas law works. So how are we going to fix this gap mathematically? How are we going to fix that gap? So we could figure out what that gap is. And instead of having PV equals nRT, we're going to have PV equals nRT plus a correction factor. And this correction factor is just some variables in here, N and B. So it's not going to be so clean. PV equals nRT is going to be PV equals nRT plus some factor. So again, look at this ideal gas law. 100 years ago, right? Then let's look at this one. Pressure versus temperature. Ideal gas and real gases work right here. At high temperatures, they match up pretty good. But at really low temperatures and low pressure, ideal gases and real gases don't match up well. Why is that? Oops. Because what happens at low pressure? Look at this, low pressure. This is low pressure. And low temperature. What happens when things are low pressure and low temperature? Are the things close together or far apart from each other? At low temperature. When it's really cold, are you going to be huddling up with your friends, try to get close to each other, or are you going to spread apart when it's cold? You're going to be really close to your friends, right? Share the heat. So when these molecules get really cold and they come closer together, do they act like a liquid or do they act like a gas? The same talk we've been talking about all semester, right? When they come close, more like a liquid. So now it's not like a gas anymore. So at these low temperatures, they don't behave like a gas. So that's why ideal gas law doesn't work for real gases, because these real gases have like a little bit of liquid property. So instead of having PV equals nRT, they're going to add a little, we're going to add a little factor. PV equals nRT and this little factor over here to make this correction, this little gap in correction at these low temperatures. Where do we get these factors from? From a table. Get these numbers. Every gas is going to have its own little correction factor, and you're going to plug it in. So instead of having PV equals nRT, nice and clean, it's going to have pressure plus this little factor times volume, and this little factor equals nRT. So when you talk about real gases, you're going to have to use this equation here. So normal gases, not under normal conditions, something like PV equals nRT is going to work. But if you want to get like a perfect number and you're dealing with like a car engine or certain high pressure situations in which you're not, your pressure and your temperatures are not normal conditions, then you want to use an equation like this. So people use type of stuff like this. People make like bombs. People make car engines. They're going to be using this stuff. It's all math now. It's pretty much standard math, algebra. Just plug in the numbers, and you could do the same thing with the PV equals nRT. Just a little bit more math intensive. So that is this chapter on gases. So gases has a big impact, right? Whether we have makes our guns, makes our explosives, makes our car engines, and PV equals nRT. Okay, we've got about 20 more minutes. Anyone having questions on this chapter, gases?
Yeah, so I noticed our two constants are Oh, it just has my question. It was the 0.0821.
Mhm.
And what was our other constant? That we, oh, an R.
That is R.
Oh, okay, so 0.8, that is R.
Yep,
And then what's the other constant?
that's it.
Oh, okay, everything else is either given or we solve for it.
Yep. So R is a constant. And, use it a few times. Let me see if I can find it here. Right here.
Isn't 22.4 a constant too?
No, that's just your calculation. You're calculating the V at STP. But if I don't give you STP or I give you a different temperature, then 22.4 is no longer a constant. It's only a constant at uh, STP. But how do we get that 22.4? We solve this equation. So, okay, so now that is chapter 9. Let's see where else. Where are we in our syllabus? About 20 minutes left, so maybe we'll. Okay, for this week. So let's start a little bit in chapter 6. Get you guys started. Electronic structure and periodic properties of elements. I don't know what that means. So let's just talk about this. So before we get into all of this, let's talk about electromagnetic radiation. Anyone's ever heard of electromagnetic radiation?
Microwaves.
Yeah, that's one example. So what does that mean? Electromagnetic radiation. What does a microwave mean? I think these are all terms you probably hear every once in a while, right? Maybe on TV or maybe in your classroom, other classrooms, electromagnetic radiation. You guys have no clue?
All light moves in a sine motion, so I guess it would be the rate at which the sine motion moves.
A lot of detail, but yeah, it basically means electromagnetic radiation is light. Light. And then how does light move? Light moves like a wave. So you mentioned like a cosine or sine wave. Yep, a wave, a repeating pattern of a wave. So since light behaves like a wave, and we know a lot about waves. Physicists knows a lot about waves. There's waves in the ocean. There's waves mathematically, cosine, sine. So what do we know about waves? There's something called the wavelength. So the shortest repeating pattern is called the wavelength. So it can mean from the peak to peak, or the bottom peak to peak, same thing, wavelength. And this wave is moving. So then there's something called the frequency. What does frequency mean? Suppose I have a little wall here. How many of these waves are going to hit this point in 1 second? That's called the frequency. The more waves hit this point in 1 second, the higher the frequency. The fewer the waves, the lower the frequency. So if you're someone right here standing in the middle, suppose you're in the ocean and there's a lot of waves. If the wave is hitting you, if a lot of waves are hitting you, the waves have a lot of energy, right? If a few waves are hitting you, then the wave has less energy. So the more waves hitting you leads to something called frequency. How many waves are hitting you per second. All right. And then there's something called wavelength. And wavelength, the unit for wavelength, it's like meter. So we're going to use a symbol, lambda, for wavelength. So what do we know about light? We're not going to get all detail about that, but basically light behaves like a particle. Oops. And it behaves like a wave. So it behaves two ways, like a particle and a wave. But for this class, we're going to focus on the wave part. And light, and this wave has some type of magnetic and electrical properties. That's why they call it electromagnetic waves, but otherwise known as light. So we just say simple terminology, just light. So it has a, we're not going to get into all this electrical and magnetic component. It's a form of energy, right? A wave is a form of energy. You ever had sunlight hit your skin? You get a little bit warm, right? That's energy. And we're going to say that this wave doesn't have a mass. It's just a wave. And it has no charge. So what do you know about waves? What we just mentioned. We know about the wavelength. And we're going to use metric system. So what is a wavelength? We could get a ruler, but a ruler is not small enough. So a lot of these waves are going to be in the nanometer, 10 to the minus 6, 10 to the minus 9 meters. Frequency, how many waves per second, otherwise known as hertz. And then when the more waves hit me, the more energy these waves have. So these units of energy is called joules, what we know from before. So think about me standing right here. Which wave has more energy? This top one, A, or this one, bottom one, B? Which wave has more energy?
The one with the high frequency?
Yeah. I'm in an ocean and every 1 second a wave is hitting me, I'm getting hit all the time, right? That's a lot of energy hitting me. If I'm in an ocean and one wave every 10 minutes is hitting me, I don't really feel it, right? So the more waves hitting me, the more energy the wave has. The less waves hitting me, the less energy it has. So look at the wavelength. Look at this wavelength. So basically, the shorter the wavelength, the more energy. The longer the wavelength, the less energy. And all waves, all light, travel at the same speed. So all these waves are traveling at the same speed, but how many of these waves are going to hit me depends on the wavelength. So short wavelength hit me more times. Long wavelength hits me less times. Which has more impact? Impact is more about the amplitude. How big are these waves? And that's also what depends what you mean by impact. But the shorter wavelength is going to have more energy. So impact, I'm not sure exactly what it means, but the one that's sometimes we're not going to talk about this class, but the amplitude, how big are these waves? They can have the same frequency, same wavelength, but then the waves are going to be much bigger. And that's maybe what you mean by impact.
Like an
So,
Richter scale.
On a Richter scale, yep. So, what types of light are there? Oh, there's a lot of different types of light. You don't think about them as light, but they are electromagnetic radiation. When you listen to your radio, how does that signal get into your radio? Through electromagnetic radiation. X-rays. Cell phone. How do you think your cell phone works? A signal has to go into your cell phone, right? Where is that signal? What is that signal? Electromagnetic radiation. So there's different types of electromagnetic radiation depending on its wavelength. So if it's really short wavelength, has high energy, then those type of things we use it for X-rays, gamma rays. You guys know what gamma rays are? Oh, you guys don't watch comics, huh? You guys know about gamma rays? You ever heard of the Incredible Hulk? That's how he became the Incredible Hulk, by being exposed to gamma rays. So there's a high energy. X-rays, high energy. Then there's a visible light. Why do we call this visible light? This region has this wavelength. Why do we call that visible light?
The only thing we can see.
Yes. When we see the microwave, the light from the microwave oven, no, we can't see it. But visible light, we can see it. So our eyes could see this region of light, which has a certain wavelength. And there's UV light, ultraviolet. You guys heard of that? So X-rays, we know that's bad for you. UV light's bad for you, right? So high energy, short wavelength, bad for you. High energy. Then we get the longer wavelength. Okay. You got your cell phone. Look at your wireless. Some of you have like a router at home, right? That's how you guys are connected. So if you guys are taking an exam by your online and you're using your Wi-Fi connection, should you have your microwave oven on?
No.
Because microwave oven and your Wi-Fi router is working under the same type of wavelength of light. So you're going to have interference. So if you guys are your internet's going down, your Wi-Fi is going bad, lost internet connection, make sure your microwave oven is off. That's going to cause interference with your Wi-Fi signal. Anyone knows how a microwave oven cooks up your food? Yeah, there's a lot of stuff you guys.
The electromagnetic to excite the particles in the food, making it heat up by moving it faster.
Oh, you're on the right track. Yeah, that's on the right track. So think about, like, you know, you've seen this TV commercial or somebody singing, and when they sing the right, right, I don't know what you call it, right pitch, they could break glass. But they sing too high of a note, they don't break it. Or they sing too low, they don't break it. They have to sing at the right pitch. You guys heard about that or know what I'm talking about? So people singing, they have to sing at the right pitch
Yes.
to break glass. If they sing too high of a pitch, it doesn't break it. Too low, it doesn't break it. So that pitch is another word for frequency or wavelength of sound. So if you hit water molecule, if you hit it the right frequency of light, what are you going to do to that water molecule? You're going to make it spin. And once you make the water molecule spin, and then what happens when you get something in your hand and you go like this to your hand? What's going to happen to your hand?
Warms
You
it.
rub your hand. Huh?
Gets warmer.
Yeah, when you rub your hands together, what's going to happen? It gets warmer. Why does it get warmer when you rub your hands together?
Friction.
Friction. That's how microwave heats up your food. You have water molecules. It makes the water molecule spin. Are we talking about one water molecule, or are we talking about Avogadro number? Right? So when this thing spins, you got a trillion of them spinning, and when they spin, they're going to be rubbing against your food, right? When they rub against your food, that's what we just talked about, friction, and that heats up your food. That's how our microwave oven works. Ah, you guys have all this stuff in your home, but you guys don't know how it works. Or some of you do know. Some of you know.
Is Bluetooth as bad as the microwaves?
All right, Bluetooth. I don't know, I have to know the frequency, but I think Bluetooth works in this region over here. Near your like AM radio type of wavelength out here. So, but before we get to that, look at the microwave. It's in the same zone as your, what did I circle there?
The deadly device in everyone's pocket.
Yep, what signal is going into your cell phone? Microwave. Okay. So sometimes you have a bad cell phone signal, maybe turn off your microwave oven too. So that's why they said, that's why some people are worried about cell phones causing cancer, because where do you put your cell phone? Next to your head. What is our body made out of? Or what does our body have a lot of? So when that signal
Water molecules.
goes into your cell phone, yeah. You think all that signal is going into our cell phone? No, some of it's going to go into our head, right? What's going to happen to these water molecules? They're going to spin. When they spin, they're going to cause some friction. Now, whether that's good or bad, don't know. Nobody really knows.
No one ever
But we'll
reads
find
the
out in about 20. Huh?
no one ever reads the book with their phones, but you should keep them about 4 inches from your body. Period.
Yep. So, and then no one really knows if this is going to be bad for you or good for you. But can you live without your cell phone now? No, it doesn't matter if it's good or bad for you. People are still going to use it, right? I'm going to get cancer in my leg because I always have my cell phone in my pocket. So that's the logic behind why people think cell phones could cause cancer. Yes, no,
They should
no, no.
create like Faraday cages in line pockets.
Yep.
But then I guess you wouldn't get calls.
Yep. So that's why people don't want to live next to a cell phone tower, right? You have a cell phone tower near your home, you're probably getting a lot of, yeah, good cell phone signal, but you're going to get a lot of radiation hitting you, right? So that's pretty much a little introduction about electromagnetic radiation. There's a lot of it out there. We use it for a lot of different purposes: X-rays, PET scans, uh, night vision, remote controls on our TVs, and so forth, right? I know a lot of people are interested in this stuff. So now you know how your microwave oven works, kind of your cell phone, and so forth. All right. So you guys are learning, now you're learning a lot of stuff, how a lot of stuff works at home. Your refrigerator, did we talk about the refrigerator, cell phone, microwave oven, cars, guns, and so forth. So since this is a chemistry class, science class, now we gotta do some mathematics, or let's try to solve some problems. So what is the speed of the light? Speed of light is 3 times 10 to the minus, 3 times 10 to the 8 meters per second. So that's a constant, call that C. And then how is the speed of light related to the frequency and then the wavelength? Speed of light equals to the frequency times the wavelength. So nu, this is called nu, this is called lambda. So the frequency is up, C is a constant. So if the frequency is up, lambda has to be down. If the wavelength is up, high, then the frequency has to be low. So these two numbers here, after you multiply them, it's going to equal to a constant. So that's why they named the speed of light C. C means a constant. So the wavelength goes up, the frequency goes down. So these two numbers are inversely opposite of each other. So how do we identify what type of light are we talking about based on its wavelength? So different wavelengths, then we give it a different name: gamma, X-ray, micro, AM, no, radio. We give it a name based on its wavelength. So now, so we know that E is proportional to frequency, right? I'm on the ocean. the more waves hit me, the higher the frequency, the higher the energy, right? So we know that E is proportional to my frequency. Higher the frequency, higher the energy. But I don't want to put a proportional sign there. I want to make this proportional sign an equal sign. How can I make energy equal to frequency? I have to put a constant, just like our ideal gas law, I have to make a constant. And that constant someone figured out is called H. E is proportional to frequency, but to make it an equal sign, I need a constant in there to make it equal. What is that constant? Planck's constant. So this guy named Planck, I guess he figured it out, or they named it after him. It's this number, 6.6 times 10 to the minus 34 joules a second. And they figured that out by doing experiments. So this is an experimental number. So E equals H nu. But what do we know about the nu? Nu equals to C divided by wavelength. So E equals H nu, we just have to put this number here into here. So now E equals to H times the speed of light divided by the wavelength. Do we know H? That's a constant. Do we know C? That's a constant. So if I know the wavelength of light, then I know the energy of that light. E equals H nu. So if we know the wavelength, we know the energy. Small wavelength, high energy, right? Just mathematically, right? Long wavelength, low energy. So light energy depends on the wavelength. And wavelength will tell us how much energy we have. Let's look at this one. Let's see how much time we have left. So light has 400, wavelength of light is 400 nanometer. What is its frequency and energy? Oh, okay. E equals H nu. What is its frequency? Oh. And what is its energy? What is frequency? We got this one right here, right? We know the speed of light? Yeah, that's a constant. Do I know the wavelength? Yeah, 400 nanometer. I put that right into here. And I just solved for that nu. So that's pretty simple. Frequency nu equals to C divided by lambdas. C is this number, lambda is this number. I got to have it in meters to cancel out that unit of meter for the speed of light. What is a nanometer? 400 nanometers, so 400 times 10 to the minus 9. I know this is not scientific notation, but it just makes my life easy because what does this mean, nanometer? 10 to the minus 9 meter. So I just do this. Meters cancel out meter. What's my answer? 7.5 times 10 to the 14 hertz or per second. This is the frequency. What is the energy of this wavelength? I just plug that into here. I know nu, I know H, I solve for E. H is this. We just solved that, nu, times those two numbers together. Our unit's going to be joules. So 5 times 10 to the minus 19 joules. So this wavelength of light has this much energy. Okay? So that's why things like over here, things that have short energy, short wavelength, they have high energy. Ultraviolet light has high energy, so when it hits your skin, it's going to damage our cells. If it damages our cells, then maybe we could get cancer. So that's why ultraviolet light is bad for us, because the wavelength is short, has high energy or higher energy, and it's going to cause some problems, or it can cause some problems. You know, this is also like, you ever seen those night vision goggles, or when our body is warm, anything that's hot, anything that's warm, it releases light. Anything that's warm, it releases light. What type of light? Heat releases something called infrared. infrared, IR light. Where is IR light on this chart? Right here, infrared light. So anything that gives off heat gives off infrared light. How do we know it gives off light? We can't see with our eyes, but we have these tools that could see the light coming off of anything that's warm. And that wavelength of light is called infrared. So we have this tool that could see that wave. Our eyes can't see it, but at nighttime, our bodies give off heat, and we have a device that could see the heat coming off of the wavelength of light coming off. And that's called infrared light. So that's kind of the principle behind night vision goggles, because anything that gives off heat, we could see it. So those police, at nighttime, you see these police helicopters chasing somebody. The police helicopter, they have this type of detector. And then they're walking down the street or going down the street, they know which car has been parked for a long time, because if the car is parked for a long time, it's nice and cold. But if they see a car that's parked on the street that's red, this red color, oh, that car is just parked there. That must mean that must be that person they're chasing, because that's the only car in the street that's hot. All right, so this is a good place to stop. It's going to get more complicated. So this is a good place to stop.